So we are talking about the lightning and profiling in this deep learning PyTorch. So this video covers about how lightning simplifies PyTorch project and how profiling helps diagnose training bottlenecks and optimize performance. So the workflow in the laboratory that we had is build a model using Lightning, train a baseline model, profile its performance, detect the bottleneck, simplify the architecture, and reprofile the optimized model. We compare the speed and accuracy trades-off. So here's a part 1, why Lightning exists. In raw PyTorch, we usually write lots of repetitive engineering code like training codes, validation loops, optimizer steps, device handling, logging, checkpointing, and distributed setup. That boilerplate distracts from the actual research. Lightning solves this by separating responsibilities into two main components. So we have the component Lightning Data Module and Lightning Module. So what is Lightning Data Module? Its responsibility is to handle data, and Lightning Module is handles model plus training logic. So instead of mixing everything in one giant script, your project becomes clean and modular. Next is Lightning Data Module. The lab creates, let's say we have the class Cypher10 data module, and its the argument is p1.lightning data module. This class centralizes all data related logic. So why this matters? Without Lightning, we manually create train loader, validation loader, and test loader, and manage datasets yourself. Lightning groups everything into one reusable object. So we instantiate them. So here's the core methods inside the data module. First is init. The purpose is store configuration settings. Like, for example, in the init argument, let's say we have the self data directory, the batch size, and the number of workers, and it stores dataset location, batch size, worker count, and transforms. Next is transform pipeline. So this performs to tensor, meaning it converts image to tensor, and we normalize it. Scales pixel values around 0. So we have the formula that its normalized value is x minus 0.5 divided by 0.5. This helps neural networks train more stably. Next is prepare data. The purpose is one-time setup task. We usually download dataset, tokenize data, and zip files. So say we have the datasets that's Cypher10, and initialize the download equivalent to true. The Lightning ensures only one process downloads the dataset. Very important in multi-GPU training. Next is setup. The purpose is to prepare datasets for actual training. It creates training split, validation split. This runs after data is downloaded. Next is train data loader. It returns data loader for training. Next is validation data loader. Returns validation data loader. And the important performance settings is number of workers. So the previous lab, it sets the Cypher10 module number of workers equivalent to 2. This means 2 CPU subprocesses load batches in parallel. Without without workers, the GPU may sit idle waiting for data. This is one of the most common bottlenecks in deep learning. Next is the Lightning module. The model is defined here, and we're going to use the Cypher10 Lightning module, and its argument is p1.lightning module. This is a class. This replaces the traditional PyTorch training scripts. So here's the key method. The init defines the layers, the loss functions, the metrics, the hyperparameters. Say we have the model architectures, the baseline model. We have the convolutional channels, and its arguments is 256, 512, and 1024, and the linear features is 2048. This is intentionally very large for Cypher10. Why? Because the lab wants you to profile a computational bottleneck. Why this model is heavy? Convolutional cost grows roughly like the input channels multiplied by the output channels and cost. So From the 256 to 200 to 512 to 1024 channels creates huge computation and memory usage. This becomes the bottleneck later. Next is forward. Defines forward propagation. Example idea, let's say we have this convolutional one and ReLU. This is identical to normal PyTorch. Next is training step. Defines one batch training step. Typically operations is we have the outputs and the loss from the, let's say we have the outputs from the self, and it contains in its argument is the images variable, and in the loss is we have the criterion function and its argument is outputs and labels. So Lightning automatically handles backward pass, optimizer step, gradient scaling, device transfer. We only return the loss. Next is validation step. Runs a validation logic, no gradients here, used to measure generalization. Next is configure optimizer. It returns optimizer. Example, we use the optimizer Adam. So the Lightning automatically use it during training. Next is baseline training. So in the previous lab we runs the helper that utils run full training, and we initialize it to the baseline returns. This trains for several epochs, so the purpose is established a baseline for speed, accuracy before optimization. Next is profiling. This is the most important concept. What is profiling? Profiling measures where time is spent during training. Instead of guessing training feels slow, we measure convolutional time, backward pass time, data loading stalls, and GPU idle time, memory overhead. Profiling turns optimization into science. So here's the profiler. We use the PyTorch profiler internally based on torch.profiler. Here is the profiling schedule. The lab profiles only specific steps. Why? The profile everything is expensive, so we only use the schedule. In the typical pace, we have the wait, warm up, and active. So the wait means do not record yet, and the warm up meaning is profiler stabilizes, and that pace the profiler stabilizes, and the pace active is we collect the traces. Next is training configuration. We set the P1 to trainer training, and key settings is max step is 14, so only train 14 batches, enough for profiling, not full training. And we set the accelerator to auto. Lightning automatically chooses GPU if available, CPU otherwise. Devices is equivalent to 1, and we use the GPU device, and we set the lagger equivalent to false and disables lagging overhead, and enable checkpointing false. Avoid saving checkpoints during profiling. So checkpoint writing adds extra overhead and preludes measurements. Running the profiler. So say we have the code training that feed and its arguments model baseline and DM loader. Just generate profiling traces. And let's read the profiler output. The profiler report shows operations like, let's say we have the operation and conv2. The meaning is the convolution. Next is convolutional backward. Its meaning is gradient computation, and profiler step is the total training step time. Here's a key discovery. The bottleneck was model complexity, not data loading, GPU starvation. The huge channel counts cause excessive computation, excessive memory movement, excessive framework overhead. Next is, let's say we build efficient model and we optimize the model changes, like the convolutional channels we set it to arguments like 32, 64, by 128, and the linear features is 512. This is much smaller. Why it becomes faster? Because smaller tensors means less memory traffic, less gradient computation, less kernel launch overhead, and better GPU utilization. Even if one convolutional kernel time changes one slightly, the entire training step becomes much faster. And here's the important insight about the bottlenecks. The lab explains something very important. The GPU isn't always slow because math is slow. Sometimes overhead is the problem. It has tensor preparation, memory allocation, frameworks orchestration, and synchronization. So large model increase this overhead dramatically. And why Cypher 10 doesn't need huge models? Cypher 10 is relatively simple. That is 32 by 32 images, only 10 classes. An oversized model wastes computation. This demonstrates a major machine learning principle, saying that bigger models are not automatically better, and architecture should match dataset complexity. Next is rep profiling. The efficient model is profiled again. Now, the profiler time drops significantly and training becomes smoother. So the GPU pipeline is more efficient. This confirms the hypothesis. That is, real optimization workflow is to measure, to hypothesize, to modify, to measure, and to validate. So when it comes to accuracy versus trade-off, finally, let's say we have the use the codes of helper utils that run full training, and the optimized model is fully trained. Then both models are compared. So here's the important key. So often, a smaller, well-designed model can perform similarly to an oversized, inefficient model, while training much faster. This is extremely important in a real-world machine learning engineering. So, to summarize, Lighting simplifies engineering. We focus on architecture, experimentation, and research instead of boilerplate. Next is profiling is essential. Never optimize blindly. We should measure it first. Next is bottleneck can come from many places. Possible bottlenecks from, like for example, from the model complexity, whether it's from the data loading, from memory transfers, synchronization, and CPU pre-processing. That's why it came from many places. Next is bigger model are not always better. Efficient architecture often give similar accuracy, dramatically faster training. So its training speed, it depends on the entire pipeline, from the disk, CPU preprocessing, data loader workers, RAM, GPU transfer, forward pass, backward pass, and optimizer step.